Hi there, Exact Education. The purpose of this video is to verify the internal resistance of a signal generator when set to sine wave 100 Hz, 7 volts RMS coming out. So we've adjusted the voltage out to give us approximately 20 volts peak to peak. Half of that is 10 volts peak. RMS is peak divided by the square root of 2. Square root of 2 would be 7.07. We've adjusted the output to give us just below, so that we've rounded it off to be 7.00 to make the numbers clearer. So open circuit, what do we mean by open circuit? There is no load on the signal generator, but what we are going to do is add progressive resistive load, single resistor load into the circuit. Current flows round a loop through the box and back again. Zero current flowing because we've disconnected the load. Open circuit voltage is 7 volts. So when we have half of 7 volts coming out, the half voltage test, we will know that the value that we've set to on our decade box will match the internal resistance of the signal generator. Why is that so? What we've done is created a voltage divider between the signal generator and a resistive load. If the signal generator internal resistance is 50 and the external is 50, we'll split the voltage in two and we'll have 3.5 volts coming out. Have a spreadsheet here to progressively bring the voltage across the load down in 10% steps, and the predicted voltages are as on the spreadsheet. And then we can see from theory what we will get is we'll get maximum power out when the load resistance equals the internal resistance. So half voltage test, so when we get the load voltage to be half the open circuit voltage, we will know that our internal resistance is the value of that particular load resistance that gives us the half voltage. So what we'll do now is we've set the decade box to 450, 400s, 510s. We'll plug it in and we get 6.3 volts coming out against the predicted value from our spreadsheet of 6.3 volts. So that does match up. The next resistance we're going to bring down to is 200. So we'll adjust the box to 200. That needs to go down to 0. We now have 200 ohms load resistance. Predicted on the spreadsheet is 5.6 volts. What we're measuring is 5.59. So we are in the real world, and obviously there's the accuracy of the resistance in the box and the accuracy of the meter to take into account. Next resistance value we've got coming down is 117. So we set that to 1, 1, 1, and this one turns round to 7. Predicted voltage is 4.90. What we have coming out is 4.84, which is very close to predicted. The next one down, we will go down to 75. So 75, that goes to 0 in the hundreds. We turn the 10s round to 70, the 1s round to 5. We've got 75. Predicted voltage is 4.20. What we've got measured on the meter is 4.23, so very, very close. So what happens if we set our box to 50, we adjust that one to 5, we adjust this one to 0, so we now have a voltage coming out of 3.49. So half voltage test would be 3.50. We're very, very close to it, 3.49. Can we do some fine tuning on the decade box to get it to 3.49? We've added 1 ohm, so we've gone from 50 to 51. and the voltage has gone up slightly. If we go up to 52, we're going too far the other way. It's 3.75. So we want to bring it back down. 52, 51. Yeah, we're just above it. Down to 50 exactly, we get down to 3.49. So between 50 and 51, we're going to 3.53. So that would suggest that the actual internal resistance is just a little bit above 50. So when we set it to 50 ohms, decade box, we read 3.49. If we jump to 51, it goes up. So I would suggest that the internal resistance is just above 50 ohms, just a little bit above 50. That assumes that this is exact on 50 and we're reading an accurate meter. When we get the half voltage test, we can see that a spreadsheet has been done to predict the power output, and what we can see is you get maximum power when the internal resistance, when the load resistance matches the internal resistance, you get a peak in the power. So we've got, in terms of milliwatts, the peak is 245 milliwatts, and you can see the values coming back down as you decrease the load resistance. So we've got about 1/4 of a watt power. We have to be careful that we were not entirely sure the size of the resistors inside the box. The assumption is that they can handle, they're big enough physically to handle 1/4 watt without overheating and getting damaged. So we've proved that the internal resistance is just a tad above 50 ohms, which is what the signal generator declares as the output impedance. So we've confirmed it's 50 ohms. Question might be, we've got a sine wave coming out at the moment. The sine wave is set to 100 hertz. Does the meter still work at 1 kilohertz? It's still giving us the same value. The RMS meter at 1 kilohertz, 10 kilohertz, it appears to be still giving us the same values. 10 kilohertz is slightly down, so it seems to be like the meter, the RMS standard digital multimeters, they will still give you the RMS value up and above 1 kilohertz, but when you get to 10 kilohertz, the value is starting to tail off, so it's not as accurate anymore. But certainly at 1 kilohertz and 10 kilohertz, the values are the same. If we go even further down, yeah, the same again, down to 10 hertz. Sorry, that's 100 hertz. 10 hertz, it's a bit off. 100 hertz, 1 kilohertz, it's the same. 10 kilohertz, it's tailing off a little bit. So we'll put it back down to 100. Thanks for watching.